Hello everyone, my name is Bartłomiej Kotua and I would like to present a piece of work which was developed as a part of my master thesis at Aarhus University and which was done in a collaboration with Ali Akbar Kamari, a doctor at the Faculty of Engineering at the same university. The title of the presentation I will talk about today is development of a BIM-based LCA tool to support sustainable building design during the early design stage. With the increasing influences of climate change on the environment, sustainability becomes the main topic of political and environmental debates. Hence, the European Union, together with the United Nations, declare a goal to reduce greenhouse gases emissions by up to 95% by the end of 2050. Only in the last century, the Earth's surface temperature increased around 0.8 degrees Celsius, and the rate of the temperature increase has nearly doubled. In reference to the report from 2014 published by Edenhofer, the building's production and operation stage are responsible for 35% of total energy use and 19% of energy related to greenhouse gases. With the increasing world population, which is expected to reach 9.8 billion by mid-2050, it is inevitable that the housing will satisfy the population needs, hence it will have a direct influence on the greenhouse gases emissions. To meet the Sustainable Development Goals, architects, engineers, contractors, together with other building stakeholders, are not only obliged to work in the building information modeling environment, but they also have to introduce the life cycle assessment concept into their practices. With our grand methods for assessing environmental impacts of the building and exploitation of the benefits of reused materials, the process of achieving the sustainable goals will be significantly hampered. Although the LCA has been widely accepted as a method to evaluate the environmental impacts of the buildings, the methodology underlying data and tools are still under development. The main disadvantages of the LCA are its complexity, time consumption, data collection, and issues with weighting. Due to those limitations, the design evaluation of environmental loads is often shifted after the design phase is completed, when all the necessary materials are available. Thus, both the possibility of influencing the design decisions made in the early design stage and the enormous potential for the reduction of the building's life cycle impacts are abundant. Since most of the available software on the construction market does not allow for interoperability between BIM environment, the most obvious solution is to integrate BIM and LCA and implement it in the early design stage to allow engineers and architects to identify hotspots of environmental impacts and minimize their effects. Therefore, the main aim of this paper is to identify and investigate current LCA and BIM integration issues, and afterwards provide a holistic framework for BIM and LCA integration, and to develop BIM-based LCA tool which can be used in the early design stage. With the decreasing of the environmental loss from the operational stage, the building material selection starts to play a significant role in the total environmental impact of the design. Thus, the LCA tool should facilitate the interpretation of the results to support the design decisions regarding material choices. Moreover, the project aims to analyze the representativeness of the data, and the outcome of that research will be incorporated into the software's architecture. In particular, the developing tool is supposed to bridge the existing gaps in current practices, which were stressed by the Exigo Consultancy, a construction company located in Aarhus, Denmark, according to the 2 rounds of the interviews we conducted with the LCA practitioners. Therefore, the developed tool in this paper should enable professionals, small architectural companies, students, and researchers to execute the calculation of the environmental loads of the building in the early design stage in a transparent, easy, and time-saving manner. The tool will allow for a fortress quantity material takeoff from the Revit model, and in contrast to other LCA tools, will allow for automated mapping of the materials to reduce the time needed to perform LCA calculations. This will lead to improving sustainable design decision processes in the early design stage, as well as to spread awareness of material selection and their production effect on the environment. Since the purpose of the tool is to being used within the BIM environment, it was an obvious choice for us to use Autodesk Revit software as a BIM platform, as it's one of the most popular architectural and engineering softwares on the market. The BIM-based LCA tool is developed using the Visual Basic Studio and C# programming language and utilization of the Revit API. The developed BIM-based LCA tool works linearly, which means that one activity needs to be finished before the other starts. The developed add-in automatically delivers the geometry extraction with the properties needed for further evaluation. After that step, The tool automatically links the elements from the material takeoff with the material database created in the Microsoft Excel spreadsheet, which was developed by the authors. The whole process of assigning Revit materials to the materials database takes less than several seconds. Of course, it may vary depending on the computational power of the station and the number of materials used in the Revit model. The material database developed by the authors is based on Okubaudat platform, which currently consists of 900 datasets in compliance with the Eurocode 1584. Subsequently, the LCA BIM-based tool calculates the total environmental impact of each material during the production phase and saves up the results, which later are displayed in the form of tables and charts. In this slide, we have the equation used for the calculation of the embodied environmental impacts, which is basically the sum of the product of every material used in the design and its environmental impact of category X resulting from a production of that material. It is worth mentioning that the process requires only one activity from the user, which is initialization of the LCA tool by clicking on its plugin icon in the Autodesk Revit software. The LCA tool displays the results in 4 ways. The first 2 are tables which represent every element used in the Revit model and its impact category result, and the environmental category loads for the whole design. When comparing the different designs and then their environmental contributions, the data displayed in the tables can be too specific while used for decision making. Thus, we introduced the other 2 methods, single score value and the pie chart. The single score determines the total life cycle impact of the Revit model as a normalized and weighted number. It supplements the first 2 methods and helps the design team to establish in a transparent way which design is better or worse. It serves as a benchmark system to which other buildings projects can be compared. Since global warming potential impact category is the most significant indicator responsible for climate change and the most common in LCA practice, we decided to add only GWP pie chart. The pie chart in this case visualizes the contribution of each material in the global warming potential impact category. The study demonstrated that there is a large opportunity to utilize BIM to perform LCA. By combining those 2 methods and introducing them as a robust tool during the early design stage, the design team has a safety margin for defining the shapes of the design. At this stage, possibilities to influence the design outcome are the highest, while the costs are the lowest. Furthermore, the study showed that even with the low detail level of BIM, there is a possibility to perform lifecycle assessment accurately enough to identify the design hotspots. The difficulties regarding the building lifecycle in the current LCA practices can be easily omitted by introducing the tool focusing only on the embodied environmental impacts of the building materials. Moreover, by emphasizing the material level LCA and the fact that the major embodied environmental impacts corresponds to the building structure, it can be assumed that the materials have the same life service length as the building. It does not only eliminate inconsistencies throughout the design, but also, as other studies indicated, it reduces the chance of delivering underreported results. Moreover, it provides a reliable solution for a quick assessment of the early stage model, which excludes the manual input of the end user. By that, the tool facilitates the comparison process, but also reduces the time consumption of the whole LCA process. Furthermore, in comparison to other existing software, the automatic mapping within the Revit platform does not require any manual input from the user. It thus takes significantly less time to obtain the results and increases the chance that environmental impacts are being considered during the design stage, as there is no additional work. Last but not least, the idea behind the development of the BIM-based LCA tool is to be used for everyone free of charges. So it can serve as an educational tool applied in university projects, consultancy companies, or in architectural offices to support the design for the environment and educate people about the importance of material selection in the design process. That does not mean that the tool is flawless. It still needs additional work in defining the model elements included in the assessment. So far, the results are material-based. Moreover, it's worth to include the other visual way of presenting the data, bar charts, bubble charts, etc. It would not only enhance comparability of the results, but also it would improve the visual aspects of the plugin. Thank you very much for your attention.